Have you ever stopped to wonder how your computer just knows things? How it can instantly tell that a valid email address is valid, but a jumble of characters isn't? It really does feel like magic, but it's not. It's actually the work of some incredibly clever, tiny conceptual machines. So let's pull back the curtain and dive into the secrets of how machines recognize patterns. It all starts with a simple, everyday question just like this one. See, behind the scenes, a program is running a very specific set of rules, kind of like a pattern matching recipe. But how do you even write that recipe? And more importantly, what happens when the patterns get way more complex? To figure that out, we need to meet our first little pattern matcher. All right, so our journey begins with a machine called a finite automaton. The best way to think of it is as a simple device that just follows a flowchart. It reads whatever you give it, one character at a time, and moves from one state or room to another based on what it sees. And there are two main flavors of this machine. Now, this is where the analogy gets really cool. The first type, a Deterministic Finite Automaton, or DFA, is like a super cautious explorer. For every single step it takes, there's only one possible path forward. It's methodical, it's predictable. The other type, a non-deterministic one, the NFA, is a parallel explorer. It can kind of magically investigate multiple paths all at the same time. Seems way more powerful, right? Well, here's the plot twist. They're not. While the NFA, the parallel explorer, is often way easier for a human to design, it turns out that anything an NFA can recognize, a DFA can recognize too. They have the exact same computational power. You can always convert one of those fancy parallel path NFAs into a systematic single path DFA. So this family of simple machines defines a very specific class of patterns they can understand. We call these regular languages. Think of things like email addresses, phone numbers, simple search terms. Basically, patterns that you can check one character at a time without really needing to remember what you saw before. So for a little while, our simple machine seems like it can do anything. But what happens when we give it a pattern that requires more than just following a simple path? What happens when it actually needs to remember something? And this, right here, is its Achilles heel. A finite automaton only knows what state it's in right now. It has absolutely no way of remembering how it got there, or say, counting how many times it's seen a certain letter. This completely memoryless nature is its fatal flaw. So let's look at a pattern that's specifically designed to break it, the language of ANBN. In plain English, this just means any string that has a bunch of A's followed by the exact same number of B's. So AB is good, AABB is good, AABBB is good, but AAB is out. To recognize this, a machine has to count the A's, remember that count, and then make sure the count of B's matches perfectly. But how do we actually prove it can't do this? Well, we use this really clever diagnostic tool called the Pumping Lemma. Think of it like a stress test or a lie detector that's specifically designed to exploit that lack of memory and prove that these machines just can't handle certain patterns. And this analogy is just a brilliant way to understand the logic. A finite automaton has a finite number of states, right? It's in the name. So imagine a house with just 5 rooms. If you take 5 steps, you could visit each room once. But what about the 6th step? You have to revisit a room you've already been in. There's no other choice. And that forced revisit creates a loop in its path. And that loop is the whole problem. Because once the machine is stuck in a loop, it can just go around it again and again and again. We can pump it. So if the loop contains an A, we can pump it to create extra A's without adding any B's. This could change AABB into AAAB or even AAAAB. The pattern is totally broken. The machine has failed the test, and we've just proven it can't handle this language. Okay, so our simple machine has officially hit a wall. To solve this problem, we don't need a whole new machine. We just need an upgrade that gives it the one thing it was missing, a memory. So say hello to the Pushdown Automaton, or PDA. It's basically our good old finite automaton, but we've bolted on a stack. Now, a stack is a really simple memory structure. Just picture a stack of plates. You can only add a new plate to the top, and you can only take the top plate off. Last in, first out. This one simple addition changes absolutely everything. To really see how this works, let's use a classic example, a palindrome, but with a C right in the middle. The machine's job is to verify that the part after the C is the exact reverse of the part before it. This is a perfect job for a stack. Okay, so as the PDA reads the first half, ABC, it does something super simple. For each character it sees, it just pushes it onto the stack. So A goes on the bottom, then B gets pushed on top of that, and finally C goes right on the very top. The stack now holds a perfect, reversed record of that first half. Now, when the machine reads that middle C, it knows the first half is over. That's the trigger. It completely switches its behavior. It goes from writing to memory, pushing, to reading from memory, which we call popping. So now, for every character in the second half, the machine checks it against whatever's on top of the stack. It reads the C and asks, is C on top of the stack? Yes, it is, so it pops it off. Then it reads B. Is B on top now? Yup, pop. And finally, it reads the A, match, and pop. And what do you know? By the time the machine gets to the end of the string, the stack is completely empty. That perfect match means the second half was, in fact, the mirror image of the first. The pattern is valid, and the machine accepts the string. That memory was the secret sauce. So this new memory-equipped machine can recognize a much broader, much more powerful class of patterns. We call these context-free languages. And yes, this includes our old nemesis AN, BN, and it's actually the basis for how most programming languages are parsed and understood by a computer. So what we've really seen today is a tale of two different machines, and each one represents a different level in a grander hierarchy of computational power. On the one hand, you've got regular languages, recognized by those memoryless finite automata. They're great for simple, repeatable rules. Then on the other hand, you have context-free languages, recognized by pushdown automata with their stack memory. The big takeaway is that adding just one simple memory component created an entirely new level of power. But there is one final, really fascinating detail. Remember how for the simple finite automata, the cautious explorer and the parallel explorer had the exact same power? Well, that's not true anymore. For pushdown automata, the non-deterministic version, the one that can explore multiple paths, is strictly more powerful. And the classic example of this is a palindrome without a middle marker, like race car. A deterministic PDA can't recognize it. Why? Well, think about it. How would it know for sure when it reached the middle to switch from pushing to popping? It can't. But a non-deterministic one can essentially guess where the middle is, and if just one of its guesses leads to a valid match, it accepts. Which leaves us with one final huge thought. We went from zero memory to a simple stack, and we unlocked a massive new class of problems we could solve. So it just begs the question, what happens next? What if we gave our machine an even more powerful kind of memory? What incredible new patterns do it even begin to understand then?